A, B, C, D, and E are running for student government positions. Their campaign posters are printed by different printing companies. The graph to the right plots each student's total price of their first batch of posters versus the number of posters in their first batch. Daniel pays $16 for 10 posters. What is the price of which is a price of $1.60 per poster? What does Cow pay per poster? Okay, so looking at this graph, Cow is C, obviously. So you're looking over here. So it's let's see here, $7 is the total price, and the number of posters I believe is 14. So that looks to me like 0.5, which is 50 cents per poster. So 50 cents per poster. Which two students are paying the same price per poster? Okay, I guess we have to do it for all of them. A, B, C, D, and E, and then we figure out which two are the same. So looking at the graph, you guys can do that. 10 over 2, that's 5. Is that 5? No, sorry, 10 over 5. It's a very expensive poster if it was the other way. So $2. Okay, so B looks like 8 over 8, which is $1. C is 7 over 14, which is what I just did, 0.5. D is 16 over 10, which is basically explained in part A. And E is 15 over 15, which is $1. So this guy is $1 and E is $1. So B and E, those two students, are the ones that have the same price per poster. In Daniel's second batch, he needs to print 40 posters. He can pay $60 to print these 40 posters at his local library. To spend less money on the second batch, should Daniel print these 40 posters at the library, or should he continue to pay the same price per poster using the company that printed his first batch? All right. So the first batch, according to the graph, it was 16 over 10, right? So that's $1.60 per poster. Okay, so that means 16 bucks gave him 10. So to get 40, you just multiply this by 4, I guess. So 4 times 16, so that's $64. Okay. All right. Pretty good there. And then at the library, the library, they tell you $60 to print 40 posters. So $60, I don't have to calculate anything to print those 40 posters. So what are they saying? To spend less money. Okay, got it. Well, just looking at this, it's $64 at that company, and then it's $60 at the library. To spend less money, he should go to the library. And finally, the last part, Annie's printing company charged $10 for her first 5 posters. Her company will charge her a lower price per poster for additional posters. Emily's printing company charges a fixed price per poster for any number of posters. By the end of the campaign, Annie and Emily each have printed 25 posters and have spent the same amount of money. What price is Annie charged per additional poster? Okay, so we got Emily and we got Annie. So Emily is $1 per poster, according to the previous calculation, and Annie is $1.60 per poster. Okay. So what are we doing here? We're going to have to figure out an equation. So let's see here. Okay, so we have to calculate this as being the same. So we're concentrating on Annie, I guess. So at the end, her price per poster has to be the same as Emily. Yeah, so Emily is $1. So whatever we calculate, it's got to be $1. So the total number of posters is 25, right? So that goes in the denominator. And the first 5 posters were $10. And then we got another 20 posters, and we don't know the price. So I guess this is the algebraic equation. Yeah. Okay, so let's solve this. So 10 plus 20x is 25. So 20x is 15, so x is 15 over 20, and that is 0.75. So 75 cents is the answer to this question. In the diagram, rectangle JKLM is drawn with its vertices on the sides of triangle PQR, so that PJ is equal to PK is 5, JQ is equal to KR is 50, KL is 40, and QR is 66, as shown. What is the length of LR? All right, so a whole bunch of Pythagoras probably, as always. LR squared is 50 squared minus 40 squared, based on, well, where's LR? This is LR, and you know, you're just using this triangle, I guess. So fairly straightforward. And if you do this math, you get LR equal to 30. What is the length of ML? Okay, well, ML, where is ML? Here's ML. It looks to me like this full is 66, right? From there to there, the whole distance is 66. And then minus 2 times LR, because LR is equal to QM, right? LR is equal to QM based on the symmetry of this diagram, actually. So this is the same as that. So, yeah. So that's basically going to be 66 minus 2 times 30. So 6 is the answer. Okay. And moving right along, C says determine the height of triangle PJK drawn from P to JK. So PJK is that little guy up there, this guy right here, and you're trying to find that height. Okay, so I guess I'll calculate the full height, so all the way going down, and then I'll subtract from that this 40, right? Okay, so whatever you want to call it, we'll just call it H. H plus 40. Yeah. Okay, so the full height, well, let's just make some labels here, probably make it a little bit easier. So PB squared is going to be LR squared. Oh, no, LB squared. Oh, okay, so LB squared looks like 30 plus 3, because it would be half of that 6. So that's 33 squared. Okay, make sure you don't make that mistake. And then plus, same thing up here. It's not 50, it's 55, because 50 plus 5, so for 55. Hold on, I think I'm doing this Pythagoras wrong here. Got to make sure that we do Pythagoras correctly. Otherwise, we won't get the right answer. Okay, there we go. That's correct. All right, so you can solve this fairly straightforward, and then PB will end up to be 44. Now, we don't want PB, we want PA. So PA is basically PB minus that 40. So it's 44 minus 40, which is 4. And finally, the part D, determine the fraction of the area of PQR that is covered by a rectangle JKLM. Okay, so the triangle PQR, that's 1/2 base times height. So base is 66, and the height was PB, right? And that's 44. So that is 1452. Okay, so JKLM, length times width, and that's going to be 40 times 6, right? Yeah, 40 times 6, which is 240. So I guess the fraction is just 240 over 1452, and I believe in lowest terms, well, whatever that is in lowest terms, and in a percentage, it's approximately 16.5%. In a Deligne sequence, the first term is a positive integer, and each term after the first is calculated by adding 1 to the previous term in the sequence, then doubling the result. For example, the first 7 terms of the Deligne sequence with the first term 4 are 4, 10, 22, 46, 94, 193, 82. The fifth term in a Deligne sequence is 142. What are the fourth and sixth terms? Okay, so let's talk about this. So we got the first term is A, let's say, right? Then you just add 1, and then you double it. So that's going to be 2A plus 2. And then again, you do this process. You add 1, so 2a plus 3. And then you double it. So that's going to be 4a plus 6. Right? And then you just keep going like this. So it's going to be 4a plus 7. Make sure I don't make any mistakes. So that's what? 8a plus 14. So now, again, you add 1, so 8a plus 15, but then you double it. So 16a plus 30. And how many do I have? 1, 2, 3, 4, 5. Let's go do one more because I need the sixth one. So 16a plus 31. And then multiply that by 2. So 32a plus 62. Correct? All right. I think that's right. Okay. So the fifth term is 142. So that means 1, 2, 3, 4, 5. So this guy is 142. So 16a plus 30 is 142. And when you solve for this, you get a equal to 7. Okay, great. So they want the fourth and sixth term. So the fourth term is this guy, which is 8a plus 14. And when you substitute a equals 7, this becomes 70. And then the sixth term, which is what they want, is this guy. So that's 32a plus 62. And if you insert a equals 7 there, that becomes 286. And I believe that is all they wanted. Determine all possible first terms which give a Dylan sequence that includes 1406. Oh boy. All right, so how far do I have to go here? So 1406. Okay, so let me just see here. So we got, let's write this out here. First term is a, then we have 2a plus 2, and then 4a plus 6, and then 8a plus 14, and then 16a plus 30, 32a plus 62, and then we'll do one more. I actually don't know how far I have to go here. Yeah, I don't know how far we're supposed to go. Well, let's do one more. I think it's, oh boy. I think it's 64a plus 126. And then we'll do one more. I think it's 128a plus 254. 256a plus 510. Okay, that's good enough. Okay, let's see what happens. So we have to calculate this for 1406. Okay, if the first term is 1406, that means a is 1406. I think what's going to happen is eventually we'll get below, eventually we'll get a non-integer, right? Because, let me see. Yeah, positive. First term is a positive integer. I got it. Okay. Okay, so then if 2a plus 2 is 1406, that means a is what? Something. It's 702. And then you just keep solving this for 1406 for each of these. I think this becomes 350, I believe. And then the next one. So far, we're all good. We're trying to find possible first terms. So these are the first terms that we find that are applicable, I guess. Wait, I got to solve this one first. 8a plus, so that's 174. And then this one, a is going to be 16a plus 30, 86. 1406, let's see here. Oh, there's an a missing here. That's going to be a is 42, I believe. And then this one, oops, that shouldn't be an arrow. These should be equal signs. This should be an arrow. 64, 86, I believe, if I haven't made any mistakes. This one, 128a. Hold on, 128. Oh, sorry, I think I did make a mistake. This is not 86. This is 20. Sorry about that. 1406 for 128a. That's going to make a equal 9. And then finally, this guy. There's an a missing here. That should be a is 3.5. Ah, okay. So this one is not valid because it's got to be an integer. So I think just those ones. So these are the possible values of A. Yeah, I think that completes the question. Okay. Part C, which possible first terms from 10 to 19 inclusive produce a Dylan sequence in which all terms after the first have the same ones digit. Okay. All right. So I guess we're given a finite number, so we have to sort of do this manually. It shouldn't be that time consuming since we're only going up to 10 to 19. Okay, so let's see here. Let's just do the first few. A, 2a plus 2, 4a plus 6, 8a plus 14. Okay. If a is 10, well, this is a. Well, I guess this column is the same. So this is a. 2a plus 2 would be 22, 46. So already these ones digits are different. So we can sort of eliminate 10. We want a sequence where all the ones digits are going to be the same for everything, I guess. I'm assuming they're saying forever. Every single. So if we can immediately see that two of them are not the same, we can eliminate that number. 11 is going to be 24, 50, so immediately we eliminate that guy. 12 is 26 and 54. Well, that goes away. 13 is 28, 58, 118. These are the same, but let's just keep this one for now because, of course, we have to test quite a few. Well, how many do I need to test here? Because they're saying which of the following, all terms. So, interesting. Okay, well, let's just keep going here. So 30, 62, well, that one fails pretty quickly. 15 is 32 and 66. That one fails. 16 is 34 and 70. That one fails. 17 is 36 and 74. That one fails. 18, 38, 78, 158. Okay, we're going to keep this one because this one looks promising. And 19 is 40 and 82, so that one failed immediately. So 13 and 18 are my candidates. And I'm just trying to think, how do you actually prove this? Because you'd have to show that it's true for everything. Do you just work with these guys here? Let me think. Or do you just say that, yeah, it's always the same. You can calculate a few more and say it's always, the units digit is always 8 based on my calculations. But there's got to be a way to prove it. Well, whatever. Maybe there is, but I'm not getting it right now. I mean, for 13 and 18, like if you did 118 plus 1 and then multiplied it by 2, it would be 119 times 2, which is 238. So it matches. Yeah, I think it's because it's always 8. So if you always take, like if you took 238 and then added 1 and then multiplied by 2, it comes 2 times 239. And again, that's going to be 478. So you can sort of just say that it's always an 8. If you add 1, it's going to be a 9. And 9 times 2 is always going to give you a units digit of 8. So something like that. I think that should be a sufficient explanation. And finally, part D, determine the number of positive integers between 1 and 2020 inclusive that can be the third term of a Dylan sequence. Okay, so what is the third term? Third term is this guy, right? 4a plus 6. Okay. So we got 4a plus 6 as our term in terms of a. And let's just see what happens when for different values of a. A equals 1, 2, 3, 4, and so on. So 4a plus 6, if a is 1, is 10, 14, 18, 22, and so on. So it looks like it's going up by 4. So Determine the number of integers between 1 and 2022. So the maximum it could be is 2020, right? So if we kept going here, 2020 divided by, let's say, what if it's 500, it would be 2006. And then it's 501, it would be 2010. 502 would be 2014, and 503 would be 2018, and I think after that it would be 2022. So for a equal to 1 to 503 inclusive, you get a number that is of the form 4a plus 6. So that means there's 503 of those. Yeah, I think that's it. Number 4, a m by n grid has m rows and n columns. Each cell in the grid is colored with either red or blue. For example, a 1 by 2 grid can be colored in 4 different ways as shown. How many different ways can a 5 by 1 grid be colored so that there are exactly 3 cells red and 2 cells that are blue? Okay, so a 5 by 1 would be, I guess, vertical like this. So 1, 2, 3, 4, 5 like this. And from the 5, we want to choose 3 to be red. And from the remaining 2, you want to choose both of them to be blue. So 5 choose 3 times 2 choose 2, which is 5 factorial over 3 factorial over 2 factorial times just 1. And that, I believe, is 5 times 4 divided by 2, which is 10. So 10 is the answer. Carrie writes down all possible colorings of a 1 by 13 grid. Looking at her first 1 by 13 grid, Carrie counts the number of cells colored red and the number of cells colored blue, and begins a list by writing down the maximum number of these two numbers. Maximum. Okay, Carrie continues this process and writes down this maximum for each of the 1 by 13 grids that she has colored. What is the smallest number in Carrie's list? All right. So we've got this 1 by 13. Let's see here. Let's see if I can make 13 of these guys. There, that's 13, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, good. So there's 2 colors, right? Blue and red. So each of these has 2 possibilities in terms of what it can be. So the total would be 2 to the power of 13 in terms of the number of different arrangements. Now the number of red cells and the number of blue cells is equal to 13, because in total there's 13 cells. Okay, so now, if that so far makes sense, let's make a list. So R, B, R plus B, and then the max number. Okay, so let's see what we got here. Okay, so this is always going to be 13, so that's always going to be 13. Now let's see what we have. You can have 0 red and 13 blue, or you can have 1 and 12 and so on, right? 2 and 11, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and 13, and then this is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that completes the table. Now, the max, this guy is the max of these 2 numbers that I wrote in this. So that's 13. That's 12, 11, 10, 9, 8, 7, 7, 8, 9, 10, 11, 12, and 13. Okay, so what they're saying is look at this column here and find the smallest number in that column. So in this whole column, the smallest number appears to be those 7s. So it's kind of a weird question. Not entirely sure what is the point, but that's the answer, I guess. Determine the smallest value of n so that no matter how a 3 by n grid is colored, it must have at least 2 columns that are colored in the identical way. All right, so it's a 3 by n. So dot dot dot. We don't know, right? So that's why I'm putting those dots. So this is 1, 2, 3, 4, all the way till n. Like that. 5, 6, whatever. And then we do know that there's 3 rows. So that's 1, 2, 3. Okay, good. Okay, so that's basically how it is drawn. Now, we know that everything is either red or blue, right? So if you just look at this one column, just this guy right here, like that, right? There's only a finite number of ways. Let me just draw it over here so don't make the diagram messy. Each of these can be either red or blue. So that means there's 2 choices here, 2 choices here, 2 choices here. So 2 times 2 times 2, that means there's 8 possible ways of making this. And I think, since I can squeeze that in, yeah, 7 and 8. Okay, that's pretty good. And those 8 are as follows. You can have either all red. I really should be using the red color, but that's okay. You guys understand. RRB. The B could be here with RR. The B could be here with RR. Or we can have one R with 2 B's. RBB. RBB. And then finally all B's. Okay. So far, all of these are different. Got it? Now what they're saying is, what does n have to be? What's the smallest value of n? So that you get at least one column that is the same. You got it? At least 2. So at least 2 meaning one other column that's the same as one of these first 8. So let's put a 9th one and see what happens. If you put a 9th one, no matter what you put here, you're going to get one of these, because there's only 8 possible ways. So one of those 8 has to go here. So for example, if I made this RBR, there you go, it's the same as that. And therefore, now you have at least 2 columns that are colored in an identical way. And that's basically what they're asking. So that happens when n equals 9. And n equals 9 is indeed the smallest value of n for which this happens.